Okay, so welcome everyone. Thanks for joining in today. Our moderator for these seminars, we've had 3 weeks of them prior to today, is Dave Clark at SFU. And so he's not here today, and that's why the email message went out late, and it's not going to be moderated in the same way as in the past. So it may be not quite as smooth today as in the other days, but I think we have an interesting topic. So Dave usually begins by saying a few words about SAG. SAG is the Sports Analytics Group at SFU. It consists of professors, graduate students, and undergraduate students who are generally interested in sports and want to apply quantitative methods to sports problems. So we've got lots of publications. We have this summer seminar series, and we hope to be even doing more as time goes on. So today's talk is on rugby league, and the technical contribution arises from functional data analysis. So let me begin by sharing the screen, or sharing my screen. Okay, no, goodness, what did I do here? Okay, like I said, this won't be as smooth as usual. There it is. All right, and I'll make that bigger. There we go. Is that okay? Can everyone see that?
Yes.
All right. So this is the first page of our paper that will very soon be completed. We're just making final touches on the paper. The title of the paper is In-Game Win Probabilities for the National Rugby League. And the players on this paper, first there's Robert. Robert, are you here today? Probably not, because Robert's from Australia, and it would be probably middle of the night. Robert is a PhD student from the University of New South Wales, and he came to us in January, just as the bushfires were starting in Australia, and then he left at the end of February, just before the pandemic set in. So Robert brought to us this great data from the National Rugby League, an enthusiasm for sport. And he's the first author on the paper. The second author is Tianyu Guan. That's Dr. Guan. She's a PhD. She's just graduated. She's defended her PhD thesis last week in our department, the Department of Statistics and Actuarial Science at SFU. And she's done most of the computing, and we've divided the talk up today into 2 parts. I'm going to speak for 10-15 minutes, and then Tianyu will carry on after that. And so she's our second author. Our third author is Jigua Cao. He's a professor in the Department of Statistics and Actuarial Science at SFU. And Jigua is a world leader in functional data analysis. Functional data analysis is roughly 20 years old, and it takes time for new methods to come into practice. And slowly but surely, FDA is being adopted in different disciplines. And this is one of the very first sports papers that use FDA. And then finally, there's myself, and I consider myself to be the conductor of the orchestra. Okay, let's move on. And this was a very enjoyable collaboration, I must say that. So here's the outline for today's talk. First, I'm going to give a high-level overview of what we've done, our contributions, the problem, and then Tianyu will come in with the technical component of the talk, and probably Tianyu will repeat a few of the things that I've said, and that's okay. It's good to hear the same thing a couple times from different perspectives. All right, so I'd like to begin by talking a little bit about rugby. And there's actually different types of rugby. The traditional form of rugby is formally called rugby union, or sometimes just rugby. And rugby union has been around for 200 years or so. It was invented in England, and it's very much a world sport. It's played everywhere. There's a World Cup that's held every 4 years, 15 players on a side. And the most recent World Cup was in November of 2019. It was held in Japan. You might have seen some of the games. South Africa won. They defeated England in the final. A version of rugby that's not as old, so it's only, I think it started in the early 90s, is rugby sevens. And rugby sevens is a very exciting game. It has only 7 players per side, and there's a league, and I'll probably get the name wrong, but I've jotted it down here. It's called the World Sevens Series. And it's held in different countries, and Vancouver actually sponsors a World Sevens event. And that's happened since 2015, 2016. And Canada has a pretty good team. Rugby sevens is quite different, 7 players a side. So everybody needs to be able to run. The game is only 14 minutes long, two 7-minute halves. It's very, very exciting. So that's the second form of rugby. Now I want to turn to 2 forms of rugby that are popular in Australia. The most popular form of rugby is sometimes called footy, Australian rules football. That's the AFL. And they have, it's the largest spectator sport in Australia. 40,000 people will attend games in Melbourne. Now, the interesting thing about rugby in Australia, in this sports mad country, is that the 2 different versions of rugby, that's Australian rules football and rugby league, which I'll talk about in a minute, they're prominent in different states. So AFL is popular, most popular in the state of Victoria. Victoria is the state where Melbourne is located, but it's expanded. So there's teams on the West Coast, teams in Perth, teams in Adelaide, and there's also teams on the East Coast in Sydney. That's a very popular sport. That's not the sport that I'm going to talk about today. In Australian rules football, they play on a very, very large field. The players are very skilled. They need to pass and kick and run. I kind of think of them as gazelles, very, very strong, very, very athletic. Rugby league is the sport we're going to talk about today. And Robert brought us the data from the NRL. He has connections with the NRL. Even though rugby league doesn't have the same number of spectators, it has, my understanding is it has the largest television audience of all the sports. And rugby league is more popular in the states of Queensland and New South Wales. So the big city in Queensland is Brisbane, and in New South Wales, it's Sydney. But it's expanded a little bit as well, and the players are a little bit different body composition than in the AFL. These guys are sort of more solid. There's players that are just real tough. They're like tanks. That's the way I kind of see it. Okay, I thought, I want to show you a clip of rugby league. Now, the problem was when I started looking at clips, it seems that all all clips, rugby union, rugby sevens, AFL and NRL look the same because in the clips, they show the scoring plays. And the scoring plays are basically running in space on a field, and all the games look similar. So I found a game, and okay, what's going on here? I want to show you, oh man, why can't I reduce this now? Oh, do I have to stop the share? Okay, this may take a moment. I have to do the share again. Okay, and then bring up. Yeah, so I want to show you Rugby League, a clip in the middle of the match. And I think in the middle of the match, this is more characteristic of Rugby League because what they do is a team will have 5 possessions. So you run with the ball and you get tackled, and or up to 5 possessions. You might score during the 5 possessions, and on the 5th possession, you may kick it away. But there's a lot of really physical play where players are bouncing into the line, and I want to show you some of that because I think it's this sort of style that distinguishes rugby league from other forms of rugby. And this clip that I have, my PhD student Lucas was able to get this for me. So here's some rugby league.
Thrown. Trainer is still with Dugan. Ball taken by Gordon, back on his 30. Now Ferguson. And Thompson comes out of nowhere and smashes into the ground.
Oh, there's some big contact in this game.
Manu. 17 is out there for the Dragons. Soleil. Third game in the top level. I think he debuted down at Lotto Land against Manly. It's Kenny Dow. Oh, friend drives it into vacant territory. It's sitting down. No.
All right, so you also saw how that works. They had the ball for 5 possessions, and then and on the 5th position, they kicked it away. So that's rugby league. Geez, wrong one. All right, it's big again. Okay, all's well. I'm a little unsure with the technology. Everybody can still hear me. Everything's fine. Nod your head, Tianyu, that everything's
Yes.
Okay, good. All right. Okay, I showed the clip, and now I want to describe to you our problem. So Robert had these conversations with the NRL, and what Robert wanted to do and what the NRL wanted to do was at the bottom of the television screen have an updating number, and that number is the probability that the home team wins. And the NRL thought that would add some excitement to the game. It would be a very small graphic. It would stay up there the entire game long. Now, what I liked about this very much was it was a very well-defined problem. My experience in doing research is if the problem is well-defined, that really helps. And so again, we wanted to have this updating probability that the home team wins at the bottom of the television screen. So obviously this would be of interest to the fans. You're watching a game, and if there's a 98% chance that your team is going to lose, you might turn off the television. The game is also of interest to punters. Punters is a UK word for gamblers, and gambling is very, very popular in Australia. You can bet at pretty much any street corner. There's a shop where you can lay a bet on a game. And so what we needed, obviously, were accurate predictions. This would be no good if we weren't able to provide probabilities that were realistic. We also need real-time calculations. It wouldn't do us any good if we had some Markov chain running in the background with thousands and thousands of iterations. We need these probabilities of teams winning to be updated continuously. And these probabilities change as the game progresses. Maybe a team scores, maybe a team, something is happening in the game that modifies the probabilities. And then finally, the work that we did, we wanted it to translate to other sports. And we think we have methods where this can be used in other sports. Okay, so what have we done? We've basically introduced FDA, that's functional data analysis, to sports analytics. And so what I want to do on this slide is make the suggestion to you that FDA, functional data analysis, is a really great tool for sports, because here you could imagine on the horizontal axis, I've got time. A rugby league game is 80 minutes long. And there's many things that you might be interested in along the vertical axis. You could be interested in possession statistics. You could be interested in the score differential, tackles. You might be interested in the number of kilometers that a player runs. So there's many problems of interest in a game of finite duration that will have functions. So in functional data analysis, the data are functions. So this line here is one one curve representing one data point, and this is another curve representing another data point. In functional data analysis, the core problem is to estimate this bold curve, and the bold curve is the mean curve. So what functional data analysis is essentially is it's not regression on points, but it's regression of functions. Okay, so one more time, I've got here a bunch of these are fictitious lines, but they're samples, and we're trying in functional data analysis to estimate the mean curve. Now, this functional data analysis is used. This is the primary tool in our work. All right. Now, I said on this previous slide that these lines are all samples, sample functions from some population. Now, the novelty of our approach is this, that we don't have a sample of functions. Games are different. In some games, maybe when you have a really strong team playing a weak team, the curve, you would expect it to be different than if two evenly matched teams are playing. So what we want to do is we want to learn from all of the matches about a match, the mean response for a given game. Okay, and how do we do that? So in rugby league and in sports in Australia and in England, like I said, betting is very, very popular. So you can go to the betting shop and you can bet $10 on the favorite, and maybe because it's the favorite, you will only receive $8 if the favorite wins. Or you could bet $10 on the underdog, and if the underdog wins, you may win not $10 back, but maybe $11 or $12 back. So those betting odds, you can play with them a little bit, and they induce a probability. So for every game, we have P naught. P naught is the probability that the we've defined it as the probability that the home team wins. these are obtained from the betting odds before the match has commenced. Okay, so we have all the betting odds, all these probabilities P naught for all of the games in our data set. In our data set, we have 4 seasons worth of data. Okay, so that's something that we have, and the idea is that games that have the core idea is that games that have similar P naughts, similar probabilities of the home team winning, will exhibit similar FDA curves. All right, now here's our only technical slide, or my only technical slide. Tianyu will have more. The problem is pretty simple. We have an event W that the home team wins. And it's this W that I'm interested in. I'm interested in the probability that the home team wins. And this W is, the probability is going to be continuously changing as the game progresses. So at the bottom here, this is the probability that I want. I want the probability that the home team wins given other variables. And what are these other variables? Well, I've already mentioned to you P naught. P naught is the kickoff probability that a home team wins. The probability that the home team wins W is going to be greater at some point in time if it's the favored team. So we have this P naught as a parameter in the problem, and we have two other variables that are important to us. D of T is the score differential in favor of the home team at time T. So as the game progresses, if the team is winning, if that differential is large, then that's going to increase the probability that they win. Now, not only does the differential affect the probability of W, the probability of the home team winning, but there's other characteristics of the game that give us insight to whether the home team will win. So I think back to that match that I mentioned earlier, the match between England and South Africa in the World Cup. I was watching that match, and it was very, very early in the match. And the commentator, I don't think there was any score yet, but the commentators were saying that South Africa was going to win. And they had determined that because of the style of play. I think South Africa was dominating the scrums at that time. So there's these variables that, in addition to the score, give us some insight as to whether the home team is going to win. So coming up with these X's is a problem for the subject matter expert, and the X's that we have in rugby league may be different than the X's that we have in soccer or hockey or some other sport. Okay, so this is our problem. The core problem that we're interested in is estimating the probability that the home team wins given XT, which is characteristics of the state of the game up to time T, given DT, that's the score differential at time T, and given P naught, that's the initial kickoff probability that the home team wins. And XT can be multivariate, so we use a univariate variable in our study, but it could be multivariate. And on the right-hand side, what I have of this equation, I've said that this is Bayes, but this is really just conditional probability. We don't use the full machinery of Bayesian inference. And the quantities that I need to be able to calculate is this one here, which is the same as this one here. And I need this one down here. And these two quantities are very similar. So it's the joint distribution of the covariates at time T, the score differential at time T, given that the home team is 1, and given the kickoff probability that the home team wins. Now, what we need to be able to do, I'm repeating myself, but we need to be able to evaluate this thing quickly. And the sole calculation of this is done using FDA methods. Okay. All right. Now I'm on to my very last slide. And this addresses the question of whether we've done anything of value. So we've got 3 seasons of data that we use to estimate this and to estimate this. And then we have a validation set, the 2019 set. So what we did for the 2019 seasons data was this. Say at the 20 minute mark of every game, we would calculate the probability that the home team wins. Okay. And then if that probability was greater than 0.5 and the home team did win, then we'd consider that a correct prediction. And if the probability was less than 0.5 and the home team did not win, that was also a correct prediction. So what we see here are the prediction probabilities for different points in time for all of the games during the 2019 season. And you can see the first thing that you notice is that as the game progresses, as we go further along in time, the prediction probability gets really high. So towards the end of the game, when you get to around the 70th minute, you know with 90% probability, we're not 90% of the time we're going to make the correct prediction. So that's all I want to say. Like I mentioned, that's just a very high level overview of what we've done. But the statistical contribution has been the use of the FDA, the functional data analysis, to obtain this term and to obtain this term. Before I turn it over to Tianyu, does anyone have a quick question for me? No? Okay, so I'll stop my share, and Tianyu, can you start?
Sure. So can you see my screen now?
Yes, I can.
Oh, nice. So thank you, Tim, for the great overview. I will follow your talk. And so for our method, basically we have the inputs, which are xt and dt and p now. So in practice, what we used for xt is missed tackle differential curve. So basically at a time t, there will be missed tackle for the home team and the road team. We're not going to use both of them, but instead we're using the difference between the home team missed tackles and the road team missed tackles. So therefore, like we will have like 2 curves. The first one is for xt, the missed tackle differential curve. And the second one is for dt, the score differential curve. So on the left, I plot xt, and on the right, I plot dt. So we can consider these 2 as curves. And also our another input is the kickoff win probability P now. And for this particular match, we have P now is 0.58. So these are our inputs. And then our output will be a curve of the in-game win probabilities. So we can see for a rugby match, we have basically around 80 minutes, and therefore we're going to have a curve for the entire match for 80 minutes. So Tim already mentioned that the objective of our research is to include a graphic at the corner of the screen. So therefore, while we are watching a match, we can see the live in-game win probabilities for the home team. So now let's see a short video. This is from a match selected from 2019 season. It is between two teams, the Storm, which is the home team, and the Bulldogs, which is the road team. So in this video, what we're gonna see is the road team will score by a try. So a try is a way for the rugby match for the players to score, and they will have like four points after a try. And we're gonna see that the road team Bulldogs will have a try and obtain 4 points. And then the probability at the corner for the home team winning will reduced. Okay, so let's see the video now. So now the player that holds the ball is from the Bulldogs. They're in white and blue. And then the home team is in a black and purple. And now they're gonna have a try. So they are over the try line and press the ball on the ground. And then the probability we see reduced from 0.8 to 0.76. So this is basically what we are trying to do. We're trying to add this graphic so that while we are watching the match, and then we have an idea like whether the home team have an advantage or not. And this is the model that team just showed us. And what we need to do by using the functional data analysis is to determine this joint conditional densities between xt and dt. So we, in order to obtain the joint densities, we will assume that both xt and dt can be expressed by a mean curve and plus the errors. And for the mean curve, mu x and mu d, we assume that they are continuous and smooth. And therefore, we're using a linear combination of the predetermined basis functions to expand it. So here, in order to estimate mu x and mu d, we are going to estimate these AKs and CKs, which are functions of this P now. And here, BK, they are the predetermined basis functions. In practice, here we use 11 basis functions. So they are cubic B-spline basis functions, and they are like piecewise polynomials, and they have degree equals to 3. And in here, this red vertical lines, they represent the interior knots for the B-spline basis functions. And in total, we have 11 B-spline basis functions. And now we notice that we assume that xt and dt, they can be represented by a mean curve plus the errors. So now in order to obtain the joint densities between xt and dt, we also need to have some assumptions for the errors epsilon x and epsilon d. So before we make the assumptions, let's first see the Miss-Taco differential and the score differentials for all the matches. So we can see on the left, we have the plots for the Miss-Taco differentials. We can see as the match proceed on, and then the variations increase. And similarly, we can observe the same pattern for the score differential. That is, as the match proceed on, the variances of the score differential and the Miss-Taco differentials increase. And Tim has mentioned that xt and dt, they are variables that up to time t. And therefore, like, we consider them as cumulative variables. So we assume that the errors epsilon xt and epsilon dt, they are errors with independent incremental contributions. And therefore, we assume that the joint distribution of epsilon x and epsilon d is bivariate normal distribution with mean 0 and variances and covariances components that are proportional to t. So this assumption also explains these two plots. So based on the joint densities for the errors, And we know that the joint distributions for xt and dt are also bivariate normal, but with the mean equals to the mean functions evaluated at time t. So here, in order to evaluate the joint densities of xt and dt, we need to estimate a case, c case, and rho sigma x and sigma d. So first, I'll introduce how can we obtain the estimate for a case and c case. So now for a particular probability p now, and we can estimate A and C by minimizing HA and HC. So we can see these two formulas, they are very similar to the smoothed kernel objective functions. And here, this 1 over Ti, this one is to accommodate the assumptions for the variances, because we assume that the variances are proportional to T for the errors. And inside here, we can see this Xi and the Di, they are the observed data, and for match I and for time points Tij. And we have the mean curves evaluated as at time Tij, but instead of using Pi now, we use P0, because for each particular match I, they are related to Pi now, but not P now. So here we have a weight that in exponential form. So therefore, like this weight, we can see we can assign more weights to matches with similar kickoff win probabilities to P now. And therefore, we can see we're basically borrow the information from the matches with similar P now. And this gamma here represent the smoothing parameter, which determines the width of the local neighborhood. We treat this gamma as tuning parameter, and we're gonna select it by cross validation. After we estimate A and C, and then we can use the estimated A's and C's and using the likelihood function to estimate the variances and covariance components, sigma x and sigma d and rho. So here we use a traditional MLE estimators. And now we know how to estimate the A's and C's, and also the variances and covariance components. So now we can use our data to see how can these values help us to obtain the in-game win probabilities. So let me repeat what data we have. So the NRL provide us with event data for 769 regular season matches in 4 seasons from 2016 to 2019. And we're going to use the first 3 seasons of event data to feed our model. And then we're going to predict the outcomes for the 2019 season. Here we randomly select a match from season 2019 and show its predicted in-game win probabilities. Here we can see the purple curve represent the in-game win probabilities that we predicted. And then the vertical dashed lines represent the scoring event. The orange vertical dashed lines represent that the road team scored. And then the green vertical lines represent the home team scored. So we can see, like, for this particular match, at the end, the home team won. And then we can see at the halftime, around 40 minutes, our predictions show that the home team win for over 90% of the probabilities. So we can see for this particular match, it's a pretty good estimate. And we know that the score the event of score is the most important while we are doing the predictions. However, in here, we also include a variable xt. So we want to show that xt actually can improve the estimate. And in order to show that, we use the same match we showed in the previous video. It is between Storm and Bulldogs, and it's from season 2019, round 4. And in order to see how XT impact the estimation procedure, we consider 2 scenarios. Scenario 1 uses both the missed tackle differential XT and the score differential DT. And scenario 2 uses only the score differential DT. And we can see on the left, I plot the in-game win probabilities for 2 scenarios. The purple curve represent the results obtained by scenario 1, and the orange curve represent the results obtained by scenario 2 using only the score differentials. And on the top panel, the gray bars represent the score differentials. And then on the bottom bar, on the bottom panel, the gray bars represent the missed tackle differentials. So we can see, like, at the end, the home team actually won. So therefore, we consider that the purple curve is always above the orange curve, except for a small interval. So we consider that scenario 1 has a better prediction than scenario 2. That means by including XT, we have like more accurate predictions for the in-game win probabilities. So we consider that XT actually has an impact on the estimation procedure. As a summary, our contributions include that we introduced functional data analysis to sports analytics, and we developed a Bayesian probability model that provides instantaneous in-game win probabilities. And the distributional components of the model can be obtained by functional data analysis estimation techniques. There are also some future works for us. For example, as Tim mentioned, we can generalize our approach to other sports. And second, because here we showed results by using a univariate XT, we can also extend our method to multivariate settings of XT. So thank you, everyone. That's all I want to present.
Great. Thank you, Tianyu. So I'm looking at the chat. So feel free to ask a question. Yeah, the one thing that you probably noticed is that the estimation procedures are quite complex, but Jigua and his colleagues have software available, not for this particular problem, but for more basic functional data analysis problems. So if you want to use functional data analysis in your sports problems, Jigua has software. Everybody's quiet. Oh, yes. Ian Schreier would like to ask a question. So please, Ian, unmute and go ahead.
Hi. We tried some functional data analysis working with injuries and activity load, and we played around with it. From a causal perspective, it was more difficult to interpret the coefficients and what we were doing. But one of the things that I said when I first heard about this is, it struck me as the only way to go in any longitudinal data set is really what we want is the functional data analysis. And yet but we use other methods because the FDA is too complicated or we don't understand the coefficient. So if I can explain that a little bit more. For me, if I'm following somebody with symptoms, because I'm working in health and pain, but you could do the same thing in running speed or whatever. There's a data generating process that is generating data every second. We are measuring at only specific points in time along whatever that data generating process is, whatever that function is. And so then we end up with these discrete pieces, and we are trying to rebuild what that actual data generating process is and then average across them. So I guess my question is this an appropriate way to think about functional data analysis? Is just you are trying to retrieve the underlying function of the true data generating process, and then it's a matter of complicated math to be able to figure that out? Or is there something fundamentally that I'm missing? Because philosophically, I think this is actually what we're always trying to do. We just can't do it.
Tianyu, would you like, oh, there's Jigwa.
Yes.
Why don't you answer that one, Jigwa?
Yes. Thank you, Tim. Yes. So I guess this is a very good question about what's the fundamental thing about the functional data. What's the main advantage for functional data? So Tim gave a very good introduction about the functional data. I think when we look at the whole trajectory as one curve or one function, the main advantage is that we are able to look at the rate of change of this function. Like we can look at the derivative of the function. So this is one advantage we can think of. Like for example, if we think about the walking, and we can look at like along the walking distance, we can look at the derivative of the walking distance will be the walking speed. And we can also look at the second derivative of the walking distance function will be the acceleration of the walking. So that's kind of a nice way to find the underlying features for the change of the function. So that's one advantage. The second advantage is that besides we look at the mean of all these curves, so we can also doing some we call the functional principal component analysis. We can look at the variations among the curves, so where the curve had the most variations appearing. So there's a lot of FTZ technique developed to do that. We can this is kind of, we also can view this as a dimension reduction. So basically, when we have infinite dimensional functions, we are able to reduce to a very low dimensional by the PCA approach. The third perspective for FDA is that we can treat this curve as one variable, and we can link this curve to other response variables. So this is we call a functional regression model. So yeah, so there's a very rich methods behind the FDA. So when we treated the function, the curve as one function, so there'll be many models, tools we can use. Yes.
Thank you, Jigwa. And thank you, Ian, for that question. Does anyone else have a question? Jigwa, you want to add more?
Yeah, I want to mention to Ian. So Ian may mention a very many people feel like FDA is too complicated. It basically, when you have these basic coefficients, and so it's hard to understand. So actually, now it's basically in my research group, we are actually working a lot about how to help the interpretation of the results. So Ian, if you want to show the result to us, I'm very happy to discuss with you how to help you to interpret your results. Thank you.
Okay, I'm looking at the chat. Lucas, you've got a question. Do you want to ask it, or do you want me to ask it for you?
Sure. Yeah, I would just ask. A great presentation. So, Guan Yu, so I have a question for you, I guess. So, is it easy or hard to quantify uncertainty, such as providing like the confidence bands using the framework of FDA?
I think so who want to answer? Tim, do you want to answer the question?
No, go ahead. Go ahead.
Yes, I think it should be okay to get the identity for the confidence bands because this is under the Beijing framework. So we are now able to find out basically the distribution of XT and WT or DT based on the FDA methods. So I think it should be straightforward to find out the kind of the posterior distributions and also the identity quantifications for the probability. Yeah, so the reason we didn't do this here, actually one audience asked our question in different talk. So Tim's answer is that we don't want to make it too complicated. You know, when in the number, the probability, win probability show in the TV, we only want to show one number. So if we give a confidence intervals, maybe many audience will get lost. Yeah. That's one concern. Yes, that's a very good point.
Yeah, I'll just add one thing. I actually think it's a very, very simple problem because the variable W, win or not win, is Bernoulli. So we know what the variance of a Bernoulli random variable is if we can estimate the P. So there you go. There's your confidence interval. It looks like Danny has a question. Danny.
Thanks, Tim. Thanks for the great presentation, everyone. I just had a quick question, Tim, on your graph where you showed kind of the validation results of how accurate the method was. You kind of have it discretized on it. Did they win or not when you said they would, I think. I was wondering if you guys looked at any kind of validation where you looked at, hey, when I said it was a 70% chance of winning, was there actually, in those cases, did the home team actually win 70% of the time? And possibly break that down by time. I know there's some football, in American football, they have in their win probability model some validation in that way where they break it down by quarters or by halves. And they say, we said it was going to win 70% of the time, and they ended up winning 69 or 68% of the time. Do you have anything like that? Or
yeah, that's a really good question. We didn't do that, but you know, there's things, as you know, called Breyer scores, and they're really easy to do.
Right.
And probably we should do that, but we just have that simple graph in there for the moment. Our paper is getting a little long. I think it's already 25 pages, but yeah, that's certainly something we should do. Yeah, thank you.
Thanks.
Saman is asked a question. Saman, do you want to ask it or?
Yeah, sure. Tianyu, nice talk. I just have a question about your tuning parameter gamma. I'm sure you may have done more work behind that. So is there any reason why you treated it as a tuning parameter without estimating using Bayesian paradigm?
That's a very good question. So can I share my screen now?
Sure.
So in here, gamma, we consider that as a smoothing parameter. So we can see that, for example, if gamma is very large, okay. So if gamma is very large, basically that means we assign like equal weights to all the observed data. And in that case, we can see that this big, very large value for gamma will result in that we're going to use like all the observed data to estimate our AK and CK. Therefore, we're gonna have a smaller we're gonna have a smaller variance but larger bias. Instead, we consider like if gamma is very small, and in this case, we can see we're basically borrow the information from the very local neighborhood. In this way, that the bias will be large. The bias will be small, but the variance will be larger. That means like the value for gamma actually determines like the like here said the bandwidth of like of the local neighborhoods that we're using, and therefore like we consider this gamma as a tuning parameter, and we're gonna use a cross validation to choose the value for gamma, and we're not gonna estimate it.
Okay, you use cross validation. I see.
So here I want to mention the for Simon, like so here I guess like we can estimate the gamma by in the Bayesian way, you know, by treat the gamma as a some parameter and we put a prior on gamma. I think we can do that. Yeah. So so we can see in the current framework, actually we are to estimate this all these parameters in the model by the frequentist method. So we don't build the model in the Bayesian way. So that's why we don't estimate. But definitely it is. I think it's possible to estimate the gamma as a Bayesian method. Maybe that will be better. Yeah.
Okay, thank you, Jigo. I have one more follow-up question actually. Did you say at the end in your conclusion that mystical differences was not significant in predicting?
No,
Yeah.
like, yeah, we want to say that this mystical differential can help us improve the accuracy of
Okay.
our result. Yeah.
Okay.
But at the same time, like the score differential is like really important. It's the most significant variable. But here we want to add one more variable so that we can increase the accuracy of our prediction.
Yeah. Okay.
Okay. So I don't see any more questions. And one of the things we're trying to do in this series is to limit our seminars to an hour. So it is 11:01 now. So I'd like to thank everyone for attending today. And I believe in 2 weeks we'll have another session, and we'll be advertising that shortly. So thank you very much. Thank you, Tianyu. Great job.
Thank you. Thank you.
Tim, I saw Alex has one question.
Oh, Alex has got a question? Okay.
Yeah.
Yes, I did, but it's
Hi.
very, very simple. Hello, everyone. Thank you very much for the talk. This was extremely pleasant and very interesting. It was very, very simple. I was thinking that you updated the probability after that in your clip that you showed us. The probability was updated after the score. So, but I guess the goal is for you to update it as the game is progressing. So I was just like, how it's actually done by the people who are actually showing the game. How often are they updating this probability, and do they do this only after big events, you know, or are they doing it like every 30 seconds? Because they can't really update like actually live, I'm thinking. So I was just curious.
Yeah. So the NRL has not implemented this yet. So we're going to be showing it to them soon.
Okay.
But you know, we have game logs, we have event data, so we have a running live values of X and also D, so we can update the probabilities as quickly as we'd like. Every 5 seconds we can do it, or probably even quicker than that. So it's all possible, but it's not being implemented right now.
So, but it is efficient enough computationally that you could do it extremely quickly, I
Yes.
guess.
Yes, that's
Because of
that
course,
was a
as time
requirement.
goes by, the probability of winning will go down if you're losing because there's less time remaining. That's not related to any major events. But yeah, that's very interesting. Thank you, guys.
Thanks.
I guess here the probability will only depend on these important events like a score or the missed tackles. So I guess this probability will not change, only change after these important events. So
Actually,
correct?
actually,
Yes.
it changes as time.
Oh, that's right. Because the
is
mean
not.
function change, right? Yes.
Yeah, but like for like events, for when there is a event for the score, and then there is a jump for the probabilities. But then if there is no big events happened, and then it still will change with time, but not that obvious.
Okay, because the underlying mean function actually is changing over time. I understand.
Yes.
Okay.
Yes. Yes.
Yeah, that's a very good point. Yes.
Okay, everyone, I'll try to shut it down now. I'll stop the recording, and thank you, everyone, and we'll see you again in 2 weeks. Cheers.